Hi guys, welcome back. This is part 2 of Hazardous Environments. If you need any more resources, check below, and hopefully this video helps you. It's full of detail. It's not just a revision piece, which is why it's so long. So let's get into it. So this part looks at volcanoes and earthquakes. Because they're very much linked as tectonic hazards, we're going to go over the cause and distribution together, and then we'll look at them separately in terms of the hazards. And then part 3 goes into the case studies of volcanoes and earthquakes. Okay, so an earthquake is seismic waves within the earth that is released when there's any movement of the lithosphere or crust. And then a volcano is a fissure or a vent that is opened up in the ground, and volcanic material then erupts from below. So let's have a quick look at how they're formed. When you're starting to explain any of these, you're going to start with convection currents. This is a very important process. Just like in the atmospheric section, we had some convection too. So if we look at the Earth's structure, we've got the inner core, outer core, mantle, and then the crust on top. So the heat is coming from the core. So just like what we can see in the diagram over here, we see there's a heat source. The thing that's being heated up in the mantle is the magma. It's becoming less dense, it's rising, it's cooling down, and it's returning then as a dense, more solid magma. And so that just starts to circulate. So those are convection currents. So convection currents are the driving force. So we would say that convection currents are moving plate tectonics due to the friction caused. You can use the word asthenosphere or just caused underneath the crust, and it moves the plates in different directions. So it starts to move these tectonic plates. The world is broken up into different tectonic plates, and where they start to break apart, they move in different ways. So in this one, we see a conservative plate boundary. So this is when two plates are either moving in opposite directions, like here at this little part here. This one's moving that way, this one's moving that way. So this creates a conservative plate boundary, and here we can see they're both moving, but one is moving quicker than the other one. So either way, what happens is friction builds up at one point in these enormous tectonic plates, and then the pressure is released, and then seismic waves start to come from that point. So sliding in the same way or opposite directions, pressure builds up and is released, causing seismic waves or earthquakes. So note at this plate boundary, the conservative plate boundary, and it also is called a transform plate boundary, we do not see volcanoes appearing here. So in a constructive or divergent plate boundary, we see that the convection currents, going back to our terminology, is pulling two tectonic plates apart. As they're being pulled apart, this creates seismic activity, of course, but it also allows the magma from the mantle to rise up to the top and potentially then to erupt out onto the surface. This creates then new land with igneous rock. So we can talk about this as seafloor spreading, as it opens up and it can drive a bigger distance between the two tectonic plates, making the sea larger. Convection currents then are what drives it underneath, and then we've got another force, we should say, is ridge push. So as the new volcanoes form new land, it's going to add weight, which pushes downwards at an angle. Magma rises to the surface and cools as igneous rock. So that is volcanic eruption, but also seismic activity or earthquakes in a constructive plate boundary. Constructive plate boundaries are all around the world. They could be at different stages. They begin as a smaller rift valley, like the one we see here. So we don't see a big sea or ocean in there yet. So this is a very young one happening here. So that is the East African Rift Valley being ripped apart. And then eventually that will cause the area here of the Red Sea to open up. And then finally we get a mid-ocean ridge where we can see that the North American and the Eurasian plate is being pulled apart, and this leaves the Atlantic Ocean. This also leaves this large ridge line, which is known as a mid-ocean ridge. We have the mid-Atlantic ridge, is in the middle of the Atlantic Ocean, which runs along the spine of the ocean. It's usually covered in water, but in Iceland, we see that Iceland rises up above it. And as we would expect, we've got lots of volcanoes dotted around Iceland on that constructive plate boundary. So that makes for a good example, and we'll actually use Iceland as a case study a bit later on. Destructive plate boundaries, or convergent, are also being driven by convection currents. There's two different types of plates. There's oceanic plates, which are more dense and will sink more in the mantle, and there's continental plates, which are thicker, less dense, which will kind of float higher on the mantle. So as the oceanic crust that's more dense goes under, We call this subduction. So it becomes subducted under there, it starts to melt and potentially allows for volcanic debris to get through. So subduction is the name of the process of the oceanic plate moving under. And then the process of slab pull, where the tectonic plate that's going under is going to drag the rest of that plate in the same direction, or encourage it to move in the same direction. So there we see convection currents moving slightly against each other. Oceanic plate is being dragged by one convection current and the continental by another one, forming a destructive plate boundary. Now, how does this relate to volcanic eruptions? Well, we have magma that's being melted off that tectonic plate. This rises up through the continental plate and then forms a volcano on the top, or potentially it happens out in sea as well. So it's either going to create a volcanic mountain on the continent or an island in the sea. So if we find that it's happening on the continent, we might see that multiple ones will follow the same. There's the plate boundary running along here, and we might get multiple volcanoes all in a row, like this one here in Chile. And this is known as a volcanic arc. And then if we're going to get it in an ocean, we would say that it is a volcanic island arc. So we can see island arcs dotted around here with the blue arrows, pretty famous places like along the Philippines, and then we see continental volcanic arcs forming in areas like this on the continental plate. So we can see this related. This creates the destructive plate boundaries around the ring of fire, creates a lot of the volcanic activity that we see around here. So we can see that this is specifically very high in density of the volcanoes in this area, and destructive plate boundaries as well. There is another tectonic plate boundary. We see the collision plate boundary. Here we will see seismic activity. So actually, just going back quickly, we should mention that in this area as well, we're going to see very big seismic activity in this zone as oceanic plates are moving under the continental, which causes lots of friction to build up and very large seismic activity there happening. Okay, fold mountains then. We have a collision plate boundary creating these fold mountains where the land might have been part of the sea, like this rock you can see here, for example, is bending around here. So at one stage this could have been perfectly straight rock strata, but because there are tectonic plates pushing against each other of the same size, they start to kind of mold and change the mountain as they collide. So we're going to see earthquakes here, but we're not going to see the presence of volcanoes. So just another plate boundary with that scenario. So far we've mentioned 4 plate boundaries: conservative, destructive, constructive, and collision. What you should do is draw out a diagram of each one and explain it in your own words using the key terminology. So that's quite an important thing to do, and just have ready and be able to identify them if you see them as coming up as diagrams, for example. When it comes to the hotspot theory then, we would imagine we've got the magma, we've got a tectonic plate, and we've got an ocean over this. This is trying to explain why do we get volcanoes in places that are not on a plate boundary. So if we look here, we have the Hawaiian hotspot, for example. So this is in the middle of a plate rather than on the plate boundaries as so many others are. So what's happening there in the Hawaiian hotspot? Well, let's imagine it thousands of years ago. We get the first formation. A magma plume, an area of concentrated magma rising up through the mantle, makes its way through the lithosphere at a certain point. This stays in the same place. This is consistently moving up and hitting this one point. So what's going to happen there? Well, eventually the magma is going to move up through the tectonic plate and it's going to form an island as the volcanic debris ends up hardening into new rock. So it creates this island then, and we're going to call this one Island 1. So Island 1 is volcanically active, but because the direction of the tectonic plate is moving, we know that convection currents overall are going to be moving the plate in that direction. So the convection currents are at work behind the scenes and they're going to move the tectonic plate. So what happens is that Island 1 is going to move with the tectonic plate into a new position, and this magma plume is going to stay in the same place and it's going to create a new island. So this happens again and again, and we see Island 1 has now moved quite a distance away. It's gotten a little bit smaller. Island 2 was formed, and even that is now too far away from the magma source, and now Island 3 is under the magma source, so it might have active eruptions there, but Island 1 and 2 might not. So this is why a hotspot is an area where we don't see it on a tectonic plate boundary, and we also see often a chain of islands, often with like dormant or extinct volcanic islands that are close by and form a line, and there's an active one then. So 1, 2, 3, moving away from the magma plume and the magma source. So that is a tectonic hotspot. And we can see the hotspot here at work. The youngest island of Hawaii then is volcanically active. The oldest island then is far away, so we know that the direction of the plate is moving that way. So this island here, the oldest island, would have been under the magma hotspot, but it has since moved away from it. And it continues away. There's lots of different islands out here. If you check it out on Google Maps, you'll see lots of islands that fit that description and follow that pattern. So this hotspot has created many islands, and the tectonic plates moving have brought the islands away from that area. Okay, so that gives us an idea as to the majority of the tectonic plate boundaries and the presence of volcanoes. It also indicates to us these gaps. Why is there tectonic plate boundaries without a lot of volcanic activity or active activity? And this comes back to the idea that they could be collision plate boundaries like up here. They could be conservative plate boundaries like this little gap here between all the volcanoes. And then we realize then that there is a big difference between the map, because those other areas and the volcanically active areas can have earthquakes, which means that earthquakes are more common. There's also little dots away from the tectonic plate boundaries as some new fault lines are opening up, and there's different things happening with collision plate boundaries as well. So there's a very good chance one of the main skills is to be able to look at this map and to be able to describe and explain why the distributions of volcanoes and earthquakes are the way that they are and why there are differences between them. Okay, let's have a look at some of the hazards associated with volcanic eruptions then. First of all, we measure volcanic eruptions in VEI, the Volcanic Explosivity Index, and you can see here that there's not a lot of modern volcanoes that have erupted that's up around like past a 5, right? Pinatubo in 1991 was a particularly recent and devastating one there, and we can see that these are mentioned, Mount St. Helens and Pinatubo here, but we see it's been a long time since we've had any eruptions of larger scale, and a couple of them we're just anticipating in the future. Some of them happened 600,000 years ago and potentially will be in the next 600,000 years. So generally speaking then, we have that covered with VEI. This will tell us basically what's happening in an eruption and how to judge the scale, and it also helps us then to anticipate what's coming in the future. On the ground then, by a volcanic eruption, we're going to see lava flow, which is the most commonly, I think, known type of eruption from a volcano. So here we see the magma, the debris that's coming from the mantle. It's appearing on the surface and becomes known as lava as it's erupting out. We can see as well that it becomes much darker as it's moving away from the source. So this could be the source of it coming out of the ground. It's flowing out here, and as it's flowing, little spots here are getting very dark. And here we can see hardened lava after it's cooled down. So we call this like igneous rock, volcanic rock, and we can see fresh lava pouring into the water here. So this is the active area in Hawaii, for example. So lava flows then can be deadly, can burn down infrastructure. Usually they can move fast, but usually they move quite slow, enough for there to be evacuations, but it can often trap people and destroy property and the environment. Ash clouds then can come in different shapes and sizes. They can cause respiratory problems in people, and they can also then disrupt things like air travel and transport. This can also, if it's a large enough scale, it can impact the climate for short periods of time or even longer periods of time, depending on the amount of ash that's sent up in the air, as it's going to disrupt the amount of radiation from the sun getting through. Pyroclastic flows then are probably the most deadly of the volcanic eruptions if you are in the vicinity of it. So here we can see that there's cloud moving down the mountain, and there's also an ash cloud moving up. So the ash cloud is moving up, light material there. So behind this cloud we would see a very thick wall of debris that's moving down, superheated, moving at 100 or 200 kilometers an hour down the hillside. So these can be absolutely brutal, and if you're in that vicinity on that slope, you are in danger. When you reach flat land, the pyroclastic flow might continue out, but maybe it might be quite reduced in terms of its velocity then, so it doesn't have the natural hill to take it down. This often happens when a volcano is about to erupt. We might see a huge part of the volcano then might be erupted, so all that debris might end up going down the slope as a mix of like a landslide with volcanic debris. So these are very deadly in the vicinity of the volcanic eruption itself. Lahars then are when volcanic debris is added to water and form a kind of large mud flow. This can be created as well, and flooding can be created through glacier being melted if there's an eruption underneath a glacier or it's passing through. The sudden addition and increase of water plus volcanic debris can cause huge issues then in terms of flooding. Or perhaps somewhere like a crater lake here might collapse due to a large eruption, and large bodies of water will be able to flow out and down the mountain on the other side. Volcanic bombs then are generally low risk unless you're very close to the eruption itself, quite small, and then pillow lava is happening underwater. Another common threat or hazard is carbon monoxide and sulfur dioxide, which is poisonous for a lot of animals. Because we can't see it as much, it's more difficult to keep track of, but it's also a good indicator if we catch it early. So in order to monitor and to predict volcanoes and looking at their, being very aware of their eruption types, it's possible to predict and to monitor, but the scale and when it's going to happen isn't exactly great. Seismic activity, which means the ground shaking or small earthquakes, is a really good indication that magma is trying to make its way through the volcano and is potentially erupting very soon. So changes in the ground around there will cause seismic activity. An increase in this would cause people to become suspicious and potentially cause evacuation of local areas. The changing shape of the mountain, as I mentioned with pyroclastic flow, so just before a big pyroclastic flow we might see a dome developing like on the side of a volcano. So when it erupts, it might erupt sideways like this as a pyroclastic flow, which is very lethal. So we would monitor any changes and deformation of the mountain very closely with things like GPS and cameras. We look at historical records, it can show us a pattern, but it also allows us to make hazard maps, which indicates to us where people are in the most danger and how we can react to that. Changes in temperature then, as it's getting a bit hotter, and volcanic gases are going to give away that there is motion and movement and changes happening in the volcano. So as I said, this could be a couple of weeks before, it could be a couple of months before, even a year before we could start to see some of these kind of changes, and it's going to be monitored more closely, but it can be very sudden, and maybe the monitoring won't pick up some of the key factors of it. So a couple of regular strategies then to do this is to monitor, as we said, warn people and to get them out. Evacuations, this is the most efficient method of reducing loss of life because we have very little to no control over the scale and the direction that the hazard is going to take. This means that this is the most efficient method to reduce the impacts and loss of life. Having damming or diverting lava flows has been implemented in places, but again, it's probably not going to be the most reliable way of dealing with this, and certainly you couldn't tell a population that they're completely safe due to damming and diverting. So the secondary hazards can start up, forest fires for example, and this can cut people off from evacuation routes or emergency services. And definitely the hazard map then is very important. We can see one out here up in the top right. So if you have an active volcanic crater in one part of the island, best to develop the other part of the island, for example, and make a red zone, which means that you're not going to allow for any of the settlements to be put there in the future. So this reduces the risk. Short-term, long-term recovery plans should be in place. More developed countries have more funding for this, and they have more supplies, and they have more technology. And they might have more information as well. So this ends up causing them to be a little bit better prepared for long and short-term recovery plans. It's also important to look at some of the benefits. So people continue to live close to volcanic areas. A lot of the debris that falls, like the tephra or the ash cloud, is going to leave the soil very fertile. Islands like Iceland have access to strong sources of geothermal energy because of the natural heat in the groundwater. Hot springs for locals and for tourists. New land being created like in Hawaii. Sulfur mining then is quite good, and other rare minerals form in these regions then with volcanic eruptions. Tourism is very big around the area, and just tradition. So people also have, like, they don't have the same assessment of risk as well, or perception of risk I should say. This means that they've lived with this risk all their lives, so they're not constantly terrified, but they learn to live with it as just a day-to-day sort of consequence of living there, and to be ready when it happens. With earthquakes then, well, going back just to the main vocabulary here, we have a focus, epicenter, fault. So the fault is anywhere like where the plate is cracked or moving, and this causes then friction to build up in this area. So the friction builds up at the focus and is released. So when that pressure is released, it releases in an energy form of seismic waves. The seismic waves move out from the focus and they reach the point above the focus first, and this is known as the epicenter. So this is the first place to get hit. So we often hear the concept of the focus and the epicenter used when we're hearing news reports or case study details. The focus then is quite an important one, because if the focus is very deep, then it has a lot of rock to get through and might be a little bit weaker and not able to do as much at the surface. But if the focus is very shallow, this means that the earthquake could be a little bit more damaging. Now, seismic waves themselves are measured in a seismograph. With a seismograph, we can go to the Richter scale and we can measure it in terms of its magnitude. So we can see the magnitude changing, 8 and up. We've gotten a couple of 9s over the past few decades, but not many have ever surpassed a magnitude 9. So this one moves up, so a 3.5 is 10 times larger than a 2.5, right? So it moves up times 10 every time. So by 10, by 10, by 10, by 10. So each one is 10 times more powerful than the one before it. And that's the way the Richter scale works. So that tells us magnitude. The Mercalli scale then is used to sort of describe the impacts more than anything. So if we had, let's say, a low-income country and we had a high-income country, they both receive an earthquake of 6.5 magnitude on the Richter scale, let's say, but the LIC is less prepared for this. So maybe the damage that is done is a 12 on the Mercalli scale, which is the highest. So let's put that in as a 12 on Mercalli scale. The HIC then is very well prepared, has lots of great architecture and things to protect it against seismic waves. So there is very little damage done and really no building collapse. So this might come in then as something like an 8 on the Mercalli scale. So this shows you the difference. So why do we measure them both differently? Well, magnitude and Mercalli scale tell a different story. Richter scale is purely looking at the physical hazard. Mercalli scale is then looking at the impacts on the population due to the seismic event. This helps us to understand the devastation, but also the help that's needed afterwards and the recovery methods that are needed too. It also helps the countries prepare for the next one to see really and gauge how prepared they are for any future events. Main hazard then, we have seismic waves, which is shaking, building destruction, infrastructure damage. We mentioned the term liquefaction. This is when the seismic wave pushes water into one area and makes the ground become a little bit more liquid, and that liquefied ground then is able to sink easily. So buildings like this could sink into the ground very suddenly as their bedrock then is changed, and the composition of the soil under it is changed to have more water. The movement of the earthquake then can cause landslides, so those themselves are hazards, but if a landslide was to enter into a lake high up in the mountains, it could cause a wave to push through the lake and down to a valley, destroying many villages along its way. It could also happen that a glacier is going to collapse in, or if it has like snow, like the snow here, if that's all along the top, this too can also fall in very suddenly. So all three of these things would cause the glacier lake to rise up and to flood lower valleys. This process is known as a glacier lake outburst flood. But generally speaking, a lot of landslides can happen too. Tsunami then is probably the most famous reaction that we have to any sort of earthquake movement. We often find that it can also happen from volcanic eruptions, landslides into the water like we just talked about on a big scale, and meteors from outside the Earth. But from a tectonic perspective, what happens is on a destructive plate boundary, suddenly what's happening is one is being subducted under the other one. Friction is released, and then the continental plate will suddenly move upwards. So the amount that it moved up is the amount of water that will be displaced and moved upwards as well. So remember, these tectonic plates are enormous. So that starts a chain reaction then of a wave moving out into the sea, which might affect other countries. But also it's going to hit the coastline that's nearest to it as well. And what happens then is shoaling, where the wave is coming in, and then suddenly as it's shallow, it's running out of space. So the wave begins to grow up instead of out. So that leads with a very large wave then coming in from the tectonic plate boundary as well. So those are the causes and distributions of volcanoes and the hazards and earthquakes and the hazards associated with both. Next one, we'll look at the 3 major case studies for lithospheric hazards. Okay, hope that helped, guys. And if it did, like and subscribe so I know that it's actually useful to you. And also just check out the resources down below. There could be something that's a bit more detailed, especially like about exam skills and how to answer them and use all of this information.